Another example, a block of the mass m equal to the 2.50 kilogram slides down a rough incline. So this we have the some friction here, right? With the theta equal to the 20 degree. So this angle 20 degree, and the mu k equal to the 0.200. With the initial speed, the v naught equal to 0.750 meter per second, and the distance d, right, 0.300 meter from the magnetic spring. So we have the magnetic spring here with the k equal to this value. So now we just want to find the maximum compression of the spring. So now you can see that this block, right, we just slide down the incline, and it's gonna spinning up until it reach the spring. Okay, so then if the block contact the spring already, the spring will be compressed, and then the speed of the block will be decreased because the spring try to push the block in the upward direction here. So the block here will move until at some point it's gonna stop. Okay, it's gonna stop. So at this position, the spring will have the maximum compression, and then at this position, the speed of the block equal to the 0. So this question is, we just want to find the maximum compression of the spring. Okay, so let's draw the picture first. Okay, so now you can see that if the block move here and then maybe to this position, oops, wait, so this is going to be the this one is going to be the equilibrium position of the spring, right? And then if oops, wait. So then if the spring is compressed to this position, okay, so if the spring is compressed to this position, we have, so okay, it's quite difficult to draw. Okay, so now you can see that at this position, the speed of the block is going to be equal to the 0 meter per second, and then here is the maximum compression of the spring. Okay, then we just want to find this x max. Okay, so let's say it's going to be the x max here, the maximum compression of the spring. Okay, so how, right? So how we solve this? We need to define the initial and the final position first. So let's say that okay, so let's say that this is the initial position of the block. Let me use number 1, right, for the initial position of the block, and then here is going to be the final position of the block, number 2. Okay, number 2. We gonna use this equation, the work done by the non-conductive force, right, equal to the K2 plus the U2, and then minus the K1 plus the U1. So don't forget that the K2 and the U2 are the kinetic and the potential energy of the system. Okay, of the system. K1 and the U1 is the initial kinetic energy and the potential energy of the system as well. Okay, so now for the K1, right, let's find the K1 first. The K1, okay, here the block we have the speed equal to the V naught, right? We have the 1/2 times the mass m, and then times the V naught square. Okay, times the V naught square. This is the initial kinetic energy of the system. In this case, we have it for the block, right? Now for the K2, it's gonna be equal to the 0. because for the maximum compression, the speed of the block must be equal to the 0, right? Otherwise the block will continue moving in the downward direction and the spring will be compressed more. Okay. Now how about the U1? Okay, how about the U1? The U1 is, okay, the potential energy, right, consists of the elastic potential energy of the spring and the gravitational potential energy of the block. Okay, but now initially you can see that the spring is not compressed or extended. It means that the elastic potential energy of this original spring must be equal to the 0, right? But now for this, for the block M1, right, you can see that it displaces from this position to this position. So it means that it has the difference in the height. Okay, it has the difference in the height. Then in this case, it must have the change in the gravitational potential energy as well. But now, what is its value? Okay, what is its value? So we need to define the reference level. Okay, we need to define the reference level here. Okay, but then which one should be a good reference level in this case? Okay, we'll just make you think first. What do you think? Which one should be the good reference level in this case? I would suggest that you can define this position to be the reference level, or you can just define this position to be the reference level as well. In this case, it means that if you define this position to be the reference level, so the gravitational potential energy of the block M, right, initially must be equal to 0 because the block M is exactly at the reference level. Okay, and then the potential energy of the block M, right, at the final position must have some value, and it's going to be negative, right, because this position is below the reference level. Okay, that's will be the first choice. And the second choice is maybe you can just define this position to be the reference level. So it means that the final gravitational potential energy of the block must be equal to 0 because it just at the reference level. But now the initial potential energy, right, of the block must be some value, and it's going to be positive because this position is above the reference level. So in this case, okay, so in my opinion, and actually what I just want to do, so I'm gonna define here to be the reference level. Okay, but actually you can just define this to be the reference level as well, or you can just define the different position to be the reference level. Okay, but in my case I will define this to be the reference level. Okay, so now if this one is the reference level, it means that the U1, right, the U1, it just depends on the M times the G and then times the height. What is the height in this case? The height is the position of the block, right, relative to this reference level. Okay, so what is this value? What is this value? Okay, if you look at this triangle, okay, so let's consider this right triangle. Okay, so let's consider this right triangle. Oops, you can see that this angle, right, equal to the theta, and this hypotenuse equal to the D and then plus the X max. But we just want to find this opposite side. Okay, so you can guess that it's going to be equal to the D plus the X max and then times what? and then times the psi theta, right? And that's it. Okay, so here we have, okay, u1 equal to the mg times the y1, right? The y1 equal to the d plus the x max, the maximum compression, and then times the psi theta. Okay, so now for the u2, the u2 is the potential energy, the final potential energy of the system, consisting of the potential energy of the block and the potential energy of the spring, right? But now of the block equal to the 0 because it just at the reference level already. But now at this position, right, the spring is compressed. It means that we must have the elastic potential energy of the spring equal to the 1/2 k and the x max square, right? 1/2 k and then times the x max square. So what else? The work done by the non-conservative force. Again, we have the friction here, right? It means that we must have the work done by the friction, which is the non-conservative force. So the work done by non-conservative force equal to minus the kinetic friction, right? The Fk, and then times the displacement. So the displacement in this case equal to the d plus the x max, okay, equal to the d and then plus the x max here. But then what is the kinetic friction? The kinetic friction equal to the mu k, right? The coefficient of the kinetic friction, and then times the normal force. In this case, normal force equal to what? Okay, actually you have seen many times, right? In this case, normal force equal to the mg times the cosine theta. Okay, if you don't remember, so just revise the force and Newton's law of the motion chapter. Okay, so we have the Fk equal to this one, and then here the work done by the non-conservative force, right, equal to the minus of the mu k, and then times the mg, the cosine theta, and then the d plus the maximum compression of the spring. Now we have everything already. We can just put everything here into this equation. Okay, so we can get that this, let me just duplicate it. Okay, equal to, okay, the k2 plus the u2, k2 just equal to 0 and the u2 equal to this one, right? 1/2 k the x max square minus the k1 plus the u1, k1 equal to this value and the u1 equal to this value. So we have the k1, the 1/2 m and the v0 square, okay, and then plus the u1 equal to this value, just the mg d plus the x max, and then no space. Okay, and then times psi theta, right? Okay, let me double check again. Equal to this, and minus this term plus this term, correct? Okay, so the next step is you need to plug in the number, right, of everything. So you need to plug in the mass m, theta, the mu k, the v0 and the d and the k, and then finally for the g. Okay, and you just solve the quadratic equation for the x max, right? So if you just keep this part because it's too lengthy, I mean just take time, right? you just solve. Okay, so plug the values. Okay, just plug the values in the variables. Okay, and solve the quadratic equations. Okay, just plug the values in the variables and solve the quadratic equation. Okay, so one will get the x max equal to the 9.43 centimeter, and that's it. So this is the answers. Okay, so just do by yourself. Okay, just put in the number and solve the quadratic equation, and you will get this value for the x max. Another examples. Okay, so consider the circular motion of the roller coaster toy car. So we have the toy car here, right, with the mass equal to the 40 gram. So it's just quite small. On a loop, right, of the radius equal to the 0.5 meter. So we have the vertical loop here. The gravity G, right, just point to this direction. Okay. Radius of the loop equal to the R, right? The forces that the track do, this must be on, do on the toy car, right, at the positions A and the B, this value. So these are the normal rotation force, right, because it's been the force that the track exerts on the toy car, right? So it's called the normal rotation force, as we have known already. So now let's say that, okay, the NA, okay, the NA here equal to the 3.95 Newton, and normal force at the point B equal to the 0.80 Newton. So now I just want to calculate the work done on the toy car from the A to the B. Okay, moving from the A to the B here, due to the resistive force. This resistive force, right, can come from the friction or the air resistance. Okay, just come from the friction or the air resistance. So let's just start from equation. The work done by the non-conservative force, right, equal to the K2 plus the U2, and then minus the K1 plus the U1. So now in this case, the point B, right, the position B is the final position. So let's change from number 2 here to be the point B. Okay, and now at the position A here is the initial position. So let's change from 1 to be the A. That's it. We just want to find the work done on the toy car from A to B. Okay, from A to B due to the resistive forces. So it means that we just want to find the work done by the non-conservative force, and that's it. How can we solve this? We need to find the KB, UB, KA, and the UA, right? We need to find the KB, UB, KA, and UA. In this case, let's find the potential energy first, because it's be the simplest thing. In this picture, right, we don't have the spring. It means that we don't have the elastic potential energy, but we have the gravity. So in this case, we're gonna have the gravitational potential energy. Let's say that if I make this, okay, to be the reference level, okay, let's just make this one to be the reference level, then we can get that the UA, right, the UA must be equal to the 0. Okay, the UA must be equal to 0 because it exactly just at the reference level. And then how about the UB, right? The UB here is going to be equal to, okay, the mass times the G, and then times the displacement from the reference level, right, equal to the 2R. Okay, equal to the 2R which is equal to the 2mg and then times the r. Okay, I think we should plug in the number to make it look easier. So we have the mass 2 mass equal to what? We have the 40 gram, right? So it's equal to the 0.0 times 10 to the negative 3. Okay, we just change to the kilogram, and then times g, the 9.81 times the r is 0.500. Okay, so the answer is 0.392 joules. So this is the potential energy of the block B, of the toy car, right, at the position B. So now we need to find the Ka and the Kb. How? Okay, how can we find the Ka and the Kb? Because we don't know the speed of the toy car, right? We don't know the speed of the toy car. So how? What we know is the normal force at the position A and the position B. Then we can link this normal force to the centripetal force. Okay, if we can find the centripetal force, it means that we can find the speed of the toy car, right, using the Fc equal to the mv square over the r. Remember from the circular motion chapter. Okay, then let's consider the position A first. Okay, so let's consider the position A first. The toy car, right? Oops. Okay, so at this position, let's draw the free body diagram of the toy car. We have what? We have the weight. Okay, we have the weight, right, equal to the mg. Okay, we have the weight equal to the mg, and then we have the normal rotation force, right, into this direction equal to the na. Okay, and let's say that the speed of the toy car at this position equal to the va. Okay, equal to the va. So in this case, from the central force, right, the Fc equal to the m v at the point A square, right, and then over the r. So now the force toward the center of the circle to be the positive, and the force away from the center, right, must be negative. Then we have the Na to be positive and the Mg to be negative. So it is the Na minus the Mg equal to the m times the Va square over the r. Okay, over the r. But we need to find what? We need to find the kinetic energy, right, of the toy car at the position A. So we said that the kinetic energy of the toy car at position A equal to the 1/2 m and the Va square. Okay, so now let's see this. We have the mVa square here, and we have the mVa square here as well, right? Then if we move the r to the left hand side and divide it by the 2, we can get the kinetic energy of the toy car. So then we have the 1/2 times the r, and then times the Na minus the Mg. So now let's just plug in the number. R is just 0.500. Okay, times the Na. The Na is the 3.95 minus the M. M is 40.0 times 10 to the negative 3 and then times the 9.81, okay, equal to, let me use the calculator, 0.25 times, okay, 3.95 times 0.04, okay, and then times the 9.81, 0.387. Wait, is that correct? Oops, sorry, my bad. This must be minus sign. 0.889. Okay, then. So now let's consider the toy car at the position B. Let's consider the toy car at the position B. Oops. Okay, then again, right, we must have the weight mg. Okay, we must have the weight mg, and what else? We must have the normal force, right? But don't forget that normal force is the force that the track exerts on the toy car. So the track is above. Okay, the track is above. So it will exert the force to the toy car into this direction. This is going to be the NB. So then again, right, the toy car is moving to the left hand side with the speed equal to the VB. In this case, we can get that the centrifugal force, the FC, equal to the M, the VB square, and then over the R, right? So the FC just equal to the NB plus the MG, okay, equal to the M, the VB square over the R. Then again, right, we just want to find the kinetic energy of the toy car at the position B. So this one equal to the 1/2 times the M times the VB square. So we have the MVB square here and the MVB square here, okay. Then it's going to be equal to the 1/2 times the R and then times the NB plus the MG, okay, equal to the 1/2. Okay, so now for the R, right, the R is just 0.500 again, and then times normal force at the point B, which is equal to the 0.680 Newton plus the M, right, the 40.0 times 10 to the negative 3 and then times the 9.81. So in this case, it's just equal to 0.68, right, and then plus 0.04 times 9.81, 0.268 joules. Okay, and that's it. So now we can combine everything to this equation to find the work done by the resistive force here, right? Then you can see that the work done by the non-constitutive force equal to, okay, the KB plus the UB, right? The KB equal to the 0.268 plus the UB equal to 0.392, and then minus the Ka plus the UA. Ka is this one, the 0.889, right? And then plus the UA, which is equal to the 0. Okay, then finally the answer is so 0.392 and then minus 0.889, 0.229 joules, right? We get equal to the minus of the 0.229 joules. Okay, so this is the answer. So now you can see that the work done by the non-constitutive force, right, or the work done by the resistive force here is negative. So this negative sign just means that the toy car, right, will loses energy, okay, during its motion. Okay, so the toy car will lose the energy during the motion, and that's it.